recording? All right. And I thought I turned on the screen and it's not on. Now it's on. Well, since we're waiting for the screen to turn on, I'm going to share with you a little bit of what I did today, what I was doing. Oh, I did. I did. The switch is 10 minutes. Okay. Now, most of you know that or some of you know that some profs, has to go from my home office, and become a virtual machine in the district. Some of you know that already. Okay. So I have to set up the virtual machine in the district. And this becomes a very comical exercise of using virtual machines. So I'm going to draw a little picture as the screen starts to warm up. So here's district office, and they have a server farm, and the virtual machine that I'm using is a virtual machine here. Okay. Sorry. And then here's my office. I have a physical machine in my office. It is running Linux. Now, in order to manage this virtual machine, VMware wants to use vSphere, which is a Windows-only client, which I don't have Windows, right? So on top of this, I'm running a Windows virtual machine. Okay. So I'm using a Windows virtual machine on top of Linux in order to manage a virtual machine that is running natively in Linux somewhere else over the network. Okay. Which is okay, except I didn't have enough space on my Linux box to have this virtual machine to run natively. This is not the only use of my Windows virtual machine. It also has plenty of other purposes. So it takes about 20 gigs of space, which by today's standard is not a whole lot. But remember, my Linux box is a pretty old machine. It was the last generation of the gateways on campus. It's one of the very few surviving gateways, on campus. It's probably one of the oldest, gateway that is still alive on campus. So the Linux box only has 160 gigabytes, which I also use, to back up the power server. So there's no space left to run the virtual machine. And this is, I forgot to bring the other setup to show you. So the virtual machine is actually living inside a little USB external hard drive, hooked up to my really slow machine using USB 2.0. And the network connection here is probably 100 megabits per second. On the other side, this is super duper. Okay, on the other side, this virtual machine is running on super duper hardware with super fast mass store and whatnot. So here comes the question. This is a blank virtual machine. In other words, it's like a PC with a blank hard drive. So how do we install something on a machine like that? Well, you need an ISO, right? You need an ISO to install the software. Okay. So I asked for some mass store on this machine that is hosting the virtual machine, which would make sense because that would make it super fast because it's right next to it. And instead of getting that, I was given the advice and say, well, why don't you use the vSphere client side CD drive to feed the CD-ROM image to the other side. Okay. So here, I have the dev live ISO sitting here on my USB 2.0 external hard drive. So in order to install the software here, dev live has to be fed through USB 2.0 to a really old Linux box through the network, which is only at 100 megabits per second, onto the other side. You can really tell because initially it's very, very slow. Anything that requires a lot of file operation is going like that. But once the program is running on the other side, you go like everything is done like really, really quickly. You can look at this way. This is a Bugatti. Is that the fastest car in the world? The fastest production car with 1,000 horsepower.
Oh, probably not anymore.
Probably not anymore. Okay, well, let's just say this is a super fast sports car, but the fuel line to the sports car is like this big. Yeah, we are delivering fuel, but very, very slowly. When it gets the fuel, go, okay, and then stop.
Reminds me of one time in Star Trek.
But anyway, I just found this is kind of comical, how they. Oh, and also there's a variety of virtual machines here too. There's a variety of virtual machines here. On this side, these are all commercial stuff, so they're all using a VMware. And then on this side, the vSphere is using VMware, but this entire virtual machine is running on QEMU. So we have a good mixture of different types of virtual machines interacting in a very strange way to make things work. Yep. Not totally related to this class, but yeah, just felt. Since I was doing this right before the class, I just felt it was comical enough to mention here. So don't feel bad when you have a bad day with your virtual machine, because things could get worse. I really particularly like the fact that I have a 1.7 gigabyte ISO file that I have to feed through USB 2.0 first, and then through a 100 megabits per second network. Yeah, that part really kind of, but it worked. See, but it worked.
You mean it's done? Actually finished? No?
Oh yeah, I was able to finish, formatting the hard drive and stuff like that. The next step is really just to copy the image over. It's not going to happen sometime in the semester, so you guys don't have to worry about the transition during the semester. But at the end of the semester, I'm going to transfer the content from my home office to the virtual box, the virtual machine that I have set up here. All right, so getting back to the stuff related to this class. Are there any questions about everything that we have talked about so far before we get into the call frame? That's the concept that we're going to talk about next. Is how do we put parameters on the stack? How do we access the parameters? I believe last time I gave you guys a brain teaser. Yep.
I'm just a little curious because we have like a practice exam on the website.
Yes. Let's talk about the practice exam first. I forgot about it.
Yeah, there's I guess.
All right, let's talk about the practice exam first. Were you guys able to access the practice exam from Google Documents? Yeah, kind of. No, nobody tried.
Yes.
No, this one is from practice exam for spring 2012. That's from that's a Google Documents. There you go. Okay, let me open it in a new tab. And here's your practice exam. I changed the format a little bit from last year because you guys don't have a computer in front of you, so these are all written answers, just like with exam 1. All right, question number 1, evaluate the partial code and then answer the question after the code. So this is the code, and the question is what operand should replace the underscores so that at label L2 the Z flag is going to be set. This has to work regardless of where the program is loaded loaded to execute. In other words, I'm asking what should I put here in order for the Z flag to set at L2. If I put a breakpoint on this RET return instruction, I want the Z flag to be set. How can I make that happen? That's the question. Well, the first thing you want to do is to really start from the beginning of the program. This is the entire program. In other words, we're not talking about a program that spans 20, 30 lines. We're talking about a program that really only have 5 instructions. So the best way to do it with a program that only has 5 instructions is to start from the beginning and then track down what is happening line by line. I will just talk about it first, and then if you guys want to, we can draw a picture as we go through these lines. We start with underscore start. That's the entry point of your entire program. So that means the first instruction that we will execute is going to be the call F instruction. What does call do? Call is going to do two things. What are the two things that it has to do? Yep.
Put the address of that location into the stack and then go to the function f.
Okay, so one is to save the return address, and the next one is to continue execution in the subroutine at the label f in this case. Okay, but what is the return address?
Start.
Nope. It is L1. There's a reason why I put a label L1 right before the no op instruction next to it. Okay? Because the no op instruction is the next instruction after the call instruction. So that means the return address is the address of the no op instruction, which in this case has a name because I call that L1. Alright, so that means L1 is pushed on the stack as a return address. Is that making any sense? After I push L1 on the stack, we will continue execution in the subroutine F. It starts with a no op instruction, doesn't really do anything useful here. And then we have the compare long instruction. What am I comparing? Not counting the unknown part here, I'm comparing to whatever the stack pointer is pointing at. What do you think the stack pointer is pointing at right now?
The address of L1.
The address L1. Okay, label L1, the value of L1. Okay, so how can I make this so that the comparison will give me a 0? In other words, how do I specify the first operand so it has the same value as the second operand?
Use L1. Use L1.
L1. Now, are we going to use L1 or $L1? $L1.
That's right, yeah.
Okay, you have to put a $L1 here, and then the comparison will give you the Z flag for sure.
ESP is being like the dereference thing, so wouldn't it be the literal address of L1 there?
Okay, well let's go ahead and actually write this code. Okay, we'll test it and go through GDB in a debugger, because the best way to illustrate this sort of thing is actually to go through the debugger. Yep.
So in the instructions there, it says it's supposed to work no matter where the program is loaded.
Yeah.
So we shouldn't assume that, because like you said on one of them, you were gonna like throw in a bunch of like 0 bytes or something, so that it would like mess up our calculations, right? So we should assume that you're not gonna like do something like that between the call and L1, right?
I can put stuff anywhere. The only place I cannot put stuff is between L1 and no op.
But if you put something between the call and L1.
Between the call and L1, yes. If I put something between call 1 and L1, call F and L1, then it's not going to work.
So you wouldn't do that, right?
No.
Okay.
If I would do that, then there's no answer to this question. There's no way you can actually specify, the proper answer in this case. If I allow you another instruction up here, then it'll be pretty easy, because all you have to do is to move L, the parent ESP, into a register, and then you can compare the register to whatever ESP points to. But based on the restriction of the question, that's not something that we can do. All right, so we'll go ahead and copy and paste. This is the first time I copy and paste from Google Documents, so we'll see whether it works or not.
Oh, gosh.
Control C, and then go to here. This is exam 2 question 1.s. And paste. Yay, sort of.
Projector is messed up a bit.
Yeah, just the indentation is missing. No big deal. We can do that.
No, if you look at the screen, it's off center.
Can we unzoom the projector?
Oh, we need to change the zoom again. Okay, I want to zoom out. It's not. No, it knows I'm trying to control it. It doesn't want to respond to it. There we go. There we go.
Thank you.
You're welcome. Otherwise, it would be very confusing. What instruction are we talking about? All right, so we have our program here, and then we'll go ahead and assemble the program, and then we'll run it. Too many memory. Oh, I forgot to actually specify the instruction. I mean the operand first. So we'll put $L1 here. There we go. Oh, I forgot one thing. It's that part. All right. So what we'll do is we'll go ahead and put a breakpoint on line 3. The no-op instruction on line 3. Okay. And then we'll run the program. Now we are on line 3. Two things to really look at. One is to take a look at ESP, the stack pointer. And the next thing that we want to look at is what is the stack pointer pointing at. So x/w, which is word in hexadecimal, and the address is specified by ESP as a register. When you use $ESP, it refers to the value of the register, and it gives us the content. In other words, at location BFFF F5AC is the content of 08048062. You know, that's the content at that location. The question is that really L1? Because our suspicion is, this is actually L1. So what we want to do is to say, print L1, and you can see, well, it complains about, a little bit. It complains a little bit because it doesn't have any type, so it doesn't know quite how to treat it. But it does tell us that L1 has a value of 8048062, which is exactly the value that we have on the stack. Okay, so now we can single step. This is the no-op instruction, and here is the compare long instruction. Single step through the compare long instruction, and then we take a look at E flags, so that we can tell whether the Z flag is set at this point, and sure enough, the Z flag is set at this point. Yep.
Are both of those considered memory operands?
No, because one is immediate. The first one is an immediate operand. When you use a $, it becomes an immediate operand. Whatever the expression is next to the $, is the value of the operand. When you have a direct operand without a $, then the expression will only give you the location at which you will retrieve the value of the operand. So that's the main difference between an immediate operand versus a direct operand. Yep.
When you have the $sign next to L1, doesn't it feed it in the address of L1, not what's at L1?
Well, L1 itself is a symbol. Okay,
Right.
To the assembler, L1 is no different than any other symbol. The definition of that symbol is the address of that no-op instruction after the call instruction.
Right.
So that's why when you use a $sign, that means I'm using that address itself as the value of the first operand.
I guess I'm confused because the ESP holds the exact same thing.
No, ESP is a register. It is merely used as a pointer.
But the content of the register, if I don't understand this, then please let me know, but it's my understanding that the content of ESP is the address where it would return to, which is L1. So when
ESP contains the address it is the address where we stored the return address.
okay, all right.
Okay, so ESP is a pointer. It points to whatever we just pushed on the stack.
All right.
But what we just pushed on the stack was the return address.
Okay.
So it's the content that ESP points to that is the same as the value of label L1. Okay. Any other questions about this particular example or sample question?
So what if it wasn't a label the next? Let's say it was like a move instruction. What would be the address of the move instruction? If instead of
It will be the same.
it'll be the same.
It'll be the
push
same.
The move
Right.
instruction address.
Yep, it is.
How would we print that?
Hmm?
How would we print in GDB the address of move instruction.
The address
So
of
if
the
we
move
wanted to-
instruction?
Yeah, like the next is, instead of we having a label there, let's say we had an instruction there, how would we print that, just to double check?
When you are there, when you set the breakpoint, it tells you the breakpoint is at a certain location.
Okay, but is there a way to print in GDB the address of a certain line?
I believe so, but I don't know the exact command to do it. There has to be a command to do that. Okay. Any other questions about this one? Questions? Then we'll move on to the next question. There are 8 questions altogether, so each one is a smaller question, but there are more questions. Okay, question number 2. What is the value in EBX, register EBX, after the following code executes? We have a push W instruction, a push L instruction, and then another push W instruction, and then we have an add instruction to ESP itself, and then we pop, and then we have another add L instruction. The last add L instruction obviously is not going to change the value of EBX. So the question is, what do you think is in EBX after the pop L instruction? In other words, what exactly is on the stack and how is it arranged by these four instructions? Yep.
Well, the first line goes in, then the second, the first W goes in, the word goes in, then the long goes in, then the word goes in, and that's the one that's going to be on top at the moment. And then you're adding 1 to that word over there. So that's the hexadecimal would be E plus 1. That's what it's going to be on there.
Well, let's go ahead and try to figure this one out. I'm pretty sure someone already has an answer, but I'm going to try to figure this one out using a spreadsheet. A spreadsheet is really the proper tool to do this. Okay. So what we'll do is we'll write the instruction on in column 1. So we'll say push W $0x624. Okay. And then the other columns will correspond to memory locations. And we'll just say that one column is 1 byte, okay? Because that's an easier way to figure out how things are, where things are. All right. So what do you think push W 0x624 is going to do to memory? Let's just say that the left-hand side corresponds to high address. No, I take it back. Yeah, the left-hand side corresponds to high address and the right-hand side corresponds to low address. So this way we are growing to the right-hand side. So of these, of this constant, what is the most significant byte? 06.
Yeah, 06.
06 is the most significant byte, and then the least significant byte is 24. Is that okay so far? And then after this, the stack pointer is going to be right here. So I'm going to format this so that we can denote where the stack pointer is pointing at. So we'll go ahead and pop this up a little bit. Is that okay so far?
Can't really see that line.
All right, fine. We'll make it more obvious. So how's that? And use a different color, green.
There we go.
How's that?
That's wonderful.
Okay, so that's where the stack pointer is pointing at. Okay, and column D has a lower address, column E has an even lower address, and we are talking about byte by byte locations here. The next instruction is push L, and it has some random value here, 6A9E22. But remember, when you push L, you're pushing 32 bits. Even though it only requires 3 bytes to represent, push L is always going to push 4 bytes. You guys have any questions?
Mm-hmm. We're trying to figure it out also.
Okay.
Sorry.
That's okay, as long as it's related to the class. So what we will do is, these two will still be here, right? It's not going to change these two. But I do have to change, this bar here because that bar is gone because we have some additional bytes. So of this particular constant, which one is the most significant byte? which has the
One thing
occupy.
before we get further, when you pulled it down, it automatically added to it,
Right.
which we're confused.
Oh, okay, it added the value. Sorry. It's trying to be very smart. Smarter than I want it to be. All right, so the next one is going to be a 0, 0 because it is implied. That's the implied most significant 2 digits of an 8-digit number. And then we have the rest, 6A. Okay, let me. 9E, and then we have 2, 2. And obviously we have to get rid of this R here and then reapply it here. There's got to be a better way to do this. There we go. Is that okay so far? So the next instruction, I think you already know what it's going to do. Push W. 0x and DE. So even though I'm only using 2 hexadecimal digits here, it's going to take up 2 bytes. It's just that the most significant byte is going to be 0, 0. So what we'll do is we'll go ahead and copy all this stuff here, and then just add the other 2 bytes, 0, 0 DE. Like that. And we also have to move the stack pointer because the stack pointer is no longer pointing here, and instead it will be located here. We change this, resize it just so that we can see everything like that. Are we doing okay so far? All right. The next instruction is add L. So add L $1 to ESP. What is that going to do? Okay, can someone remind me, how do we read the columns? The ones on the left are the ones with a higher address or a lower address?
Lower address.
Higher.
Higher address, okay? Because we're growing the stack to a lower address location. So this is kind of counterintuitive because when you use GDB, it prints out memory content in exactly the opposite order. But it's not friendly, for display purposes like this one here. So if I add 1 to ESP, what should I do to change this picture here?
Green bar will be moving left.
Yeah.
We have to move the green bar 1 cell to the left. Okay,
It's only 1 cell.
only 1 cell, because we are only adding 1, and the memory location is byte addressable.
Okay.
Because it is byte addressable, so we only want to move 1 single byte. So now we have the green bar moved to here instead of here. Are we doing okay so far? Now here comes the instruction that is important. Pop L EBX. Now pop L EBX, is going to do something to the stack pointer, but it's also going to do something to EBX. So what I want to do is to shade the 4 bytes that we are going to put into EBX, and then move the bar, over to wherever it is supposed to go. Which 4 cells should I, or which 4 columns should I highlight in this case?
E through H.
Say again?
E through H.
Okay, so we want to highlight this byte. This is the least significant byte. Next one, next one, next one. These 4 bytes. So what I'll do is I'm going to shade these bytes. And let's see, change the background color to something like that. And at the same time, I also have to change the bar because it is no longer at this point. So go to borders, get rid of this. And instead it will be moved to here. So format the cells again. And change it to green here. Okay. So what is the content of EBX?
6A9E2200.
Exactly. Okay. Because this time we are listing the byte content, high address is on that side, low address is on the other side. So the way you read it is really just the way it is displayed here, because we are listing high memory content on the left-hand side, which is the same as the most significant byte on the left-hand side. So the content in EBX really should be 6A9E2200. Yep.
The address on the right side is below the stack, but is it still there after you popped it?
Which row are you referring to?
The last
Row 4?
The last row.
This row?
The address on the right side of the ESP pointer.
He's talking about column line.
Below the pointer.
You mean here?
Yeah, and the left side that's highlighted too.
Well, if no one bothers this program, yes, that content should still be there, but you cannot count on that content still being there.
What about the pop address?
The pop operation does not destroy the content on the stack. All it does is to retrieve whatever the stack pointer is pointing at and put it into somewhere else, and then change the stack pointer. But it doesn't really do anything actively to destroy the content that is already on the stack.
So if you don't have anything overriding the address, it'll be there.
If you have something that can override the address, yes, then it can happen. Does anyone know whether signals will use the user space stack or does it use the system stack? Nobody knows? Okay. I can just Google it. Okay. Signal.
Who's talking to you?
It's okay. Okay. Signal stack. There are two interfaces for telling the system to use a separate signal stack.
Signals don't use this. We're not using normal stack.
Does it use a user stack or a signal stack?
The signals don't use this. From what I know, the signals themselves don't use the stack at all.
Well, signals have to use a stack because it has the ability to go back to where it was interrupted. Well, anyway, getting back to our program here, the point is, everything that is on the other side of the stack pointer is fair game to be corrupted by something else. Okay, so you cannot count on that content to still be there. Are there any questions about this question? Because that's the answer. The highlighted 4 bytes is the answer of this question. Is that okay?
Maybe silly more.
Can we run it just to make sure?
Hmm?
Can we run it just to make sure?
Can we run it?
Wait, can we go over the last instruction before you do that? I just
Last-
want to.
Sure.
I mean, I know that's not part of the answer, but
No, that's fine. I think it's a good question. The last instruction is add 3 to ESP. So what it's going to do to our spreadsheet is really just to move the green bar. So add $3 to ESP. Everything will still be the same here, except the green bar will change because I'm adding 3 to the stack pointer. So the stack pointer will be pointing 3 bytes higher than it was before. So that means the green bar will no longer be here, and instead it will be here. Is that okay?
yeah. Okay. So
There is stuff.
when
Okay.
you pop those, it's not popping them actually off the stack. It's just putting them in
Correct.
EBX.
I did not pop the content into something else. I merely changed the stack pointer so that stuff is quote unquote gone.
Well, I just thought when you did the pop L EBX, it would pop the green highlighted bytes or whatever.
It did copy that into EBX, except EBX
But
is not
I thought it
displayed.
would take it out of the stack. I don't know why.
Well, remember the move instruction, what I talked about, with the move instruction, there's a misnomer because you cannot move bytes from one location to the next. You can only copy the content from one location to the next.
Okay.
So as a result, when we are popping content from the stack, it's the same thing.
copy.
All we are doing is copying that content into a register
stays.
or a memory content location, but we are not destroying the content at that location. But we do have to move the stack pointer to
Right.
remember that, okay, this content is not a part of the
Right,
stack anymore.
right.
Logically, it's not, but in terms of physically, yes, it is. Chances are it is still there, at that time after you pop it.
Okay, that's what I needed to know.
Okay. Any other questions? Yep.
I had a question. Why are you using for that add long? Does it matter in that case?
Add long versus add word.
No, because it's ESP, right? It already assumes it's
It is.
32-bit.
It's because it's ESP. The stack pointer only has a 32-bit, format instead of. It doesn't have. It doesn't have like SPL, SPH, like AH and AL, for one thing. But the second thing is the stack pointer is a pointer, and because I'm running this on a 32-bit architecture, that means every pointer, every address is 32-bit long.
Yeah, but if you just use the add instruction, it would still work instead of the long.
Yes, if I use just add $3 to ESP, it would work exactly the same way, because when I say the name ESP, it implies it's a 32-bit register. Yes. But I always like to make sure that I use the correct width of operation, so I don't use anything that is implied. Yep.
If I use add W or byte, would it crash?
The assembler would not let you get away with it. If you use add W instead of add long in this case, then you have an inconsistency. Because on one hand, your instruction, the mnemonic of the instruction is implying it's a 16-bit operation, but when you look at the second operand, it is a 32-bit operand. So there's a disagreement between the mnemonic and the operand. So the assembler is smart enough to at least give you a warning in this case, if not an error. Yep. It should be an error, yes, but sometimes it only gives you a warning. Yep.
Would you be able to edit the contents of that location through ESP? Would you be able to?
Yes, you would.
How would you add, for example, like to the 00 byte at the end of there? How would you add?
Can you name the cell? They're like H7 or something.
H7, yeah.
Yeah, you can do that.
Well, because you're using the $3 to add.
Well, let's write another instruction here, assuming nothing is changed on the stack. Okay, that's a big assumption there. It's a big assumption because in this type of situation, you almost will never see the content of the stack being changed, even though the stack pointer is not pointing to it anymore. And that's only because your operating system is intercepting all the interrupts, all the hardware interrupts and all the software interrupts. So it never affects your own stack. The system stack is being modified when interrupts happen. But on the other hand, if you're using an architecture that has no operating system or a non-protected operating system, whenever you have an interrupt happening, it's going to corrupt, I shouldn't say corrupt, but it is going to use your stack to remember where to return to. So that means anything on the other side of the green bar, like these content here, can be changed. And you don't know whether it's going to be changed or not because it depends on when the next interrupt is going to happen. But yes, the answer is yes, you can change all these locations because ESP can appear inside the parentheses. So you can access ESP using the indirect mode. You can also use it as a base register. You can use it as an index register if you want to. So so all the other addressing modes that we have talked about, you can utilize ESP to control where you want to change the content. So yes, you can change content on the stack just as easily as any other memory content.
Because I was thinking if you would do the add L3 to like EBX, for example, it would actually add literally 3 to the value of the EBX.
Yes.
But in this case, it just adds the it moves the pointer instead of adding.
Well, I am changing the value of the stack pointer. It's just that I never truly represent the value of the stack pointer because it doesn't really matter in this case. It's only the relative change of the stack pointer that is important in this example, not the actual value of the stack pointer. Okay? So this is the, I'm capturing this, as a spreadsheet, but if anyone is interested and want to do it on your own, you can also, go through this code in GDB and you will see exactly the same thing happening. When you look at ESP and also the content on the stack, you should see exactly the same thing happening. So I'm going to use, yep, go ahead.
So when we push something onto the stack, we are not thinking about like little endian, like it goes directly as it is. So
No, okay. The question was, when we push something on the stack, do we have to be aware of little endian versus big endian? The answer is yes, absolutely. Okay.
Right here, where
And that's only because I changed the way, I point memory. Okay, let me just be very, very clear here. Okay, high memory goes this way. Okay, and that's why everything looks just right this time. It's only because the left-hand side has the high memory address, and then the right-hand side has all the lower memory addresses, because I changed the ordering. If I did not change the ordering, then it will be much harder to draw the stack out, because then I have to plan ahead of time and know how many bytes I need to use in order to grow it in the proper direction. Is that okay? But this is important. Being able to visualize, the stack, is a very important step to understand not only the stuff that you need for the second exam, and actually for everything that we will talk about, to the end of this semester. Any questions about this one before we move on? No questions? So as I said, it is probably a good idea for you guys to try out, just write a program in GDB, trace the program in GDB, look at how ESP is getting changed, and look at how the content on the stack is getting changed as well. So that would be useful. Yes.
Just a quick question. Where do you put these files under, like this week's lectures?
I usually don't upload these files,
Okay.
but if you want me to upload, you can just send me a reminder, and I'll pack it up and send it up.
Fine.
I'll have Scotty to beam you up. I remember your Star Trek reference a little bit early.
That's because I remember you first one the first day, so I was like, oh, you found it out. It's on now.
All right. So that's question number 2, and here's question number 3. The unconditional jump instruction can be, quote unquote, clumsily replaced by the return instruction, but it has to have another instruction to help it. Okay? And you have to choose whether it's before or after the return instruction. Assuming the return instruction is assuming the jump instruction to replace is jump to label L1, what are the 2 equivalent instructions, one of which is a return? And this time, the order is important. Okay. In other words, I'm asking you, let's say I have a strange computer architecture that has no unconditional branch instruction. Very weird. But it has everything else that we have talked about. Okay? So the question is, how can I emulate a unconditional branch instruction using the other instructions that we have talked about, one of which is the return instruction? Yep.
Do you pop L1 on there and then use return after that?
You are close.
Close, okay.
Yep. Sorry?
Push the address and return.
I'll
Yep, push
it.
the address
Sorry.
first.
Push
Okay.
it.
You said pop. I think you actually knew the answer,
knew
but
it.
you just used the wrong word.
Okay.
Yep, that's exactly right. Okay, the answer is use push L first, but you have to push $L1. Do not use L1, because if you say push L1 is without the dollar sign, then what you're pushing on the stack is the content at address L1, which is not what you want to push. And then the next instruction is just the return instruction itself. In other words, you are pushing an address on the stack and then tell the computer immediately and say, oh, guess what? Use the 4 bytes that I just pushed on the stack and continue execution at, use that as an address and continue execution at that address. Is that okay so far? And this one you can also test very easily. Write a very simple program. Replace a unconditional branch instruction with these 2, and you can see exactly what is going on. Are there any questions at this point about number 3? No questions? Okay. move on to question number 4. Describe what the following instruction does. Note, the operand is determined before the action, however, the effect on ESP is applied after the action. Okay, I know it looks a little bit confusing because the push out instruction itself implicitly will use ESP for a few different for its own purposes. But the operand in this case is also using ESP. So the question is, what exactly is this instruction doing? Yep.
Making a duplicate of the address already there.
Is making a duplicate of the content already there. Only the content, not the address.
And then it's moving, ESP gets moved 4 bytes.
Correct. In other words, we are duplicating the last item, the last 4 bytes pushed on the stack.
And this subtracts 4.
And yes, the stack pointer will be decremented by 4. Okay. Any questions about this one before we move on? I mean, it's really just a verbal description of what it does. Yep.
So basically, since ESP is pointing to the first part of the stack, and you're pushing the address that is in that place.
Not the address, the content, because the operand here, this is an indirect operand, which means I'm not interested in ESP itself. I'm interested in the 4 bytes that it points to. So it will first retrieve the 4 bytes that ESP points to, copy those 4 bytes into a place that has no name because it's not in a register of any kind, but it's a buffer, okay, of some kind. And then what it will do is it will first allocate 4 bytes on the stack by changing the stack pointer at that point, and then copy the 4 byte buffer into those 4 byte locations. So therefore, it's what this is just duplicating or cloning or copying the last 4 bytes on the stack. Okay. Any questions about this one? Yep.
I don't have a question about this, but it's about the test.
Mhm.
It's going to be all short, simple question like these, or
Yeah.
the small one where he has a program.
Do you prefer the long ones? I think the short ones are better. Okay. I think the short ones are better because each one only tests a particular aspect of using the stack, call, return, and stuff like that. So if someone has a misunderstanding of one particular instruction, yes, that question will be gone. But there will be many other questions where people can get points. So that I think this is better. It's easier on you guys and easier on me too because grading will be a whole lot easier.
Thank you.
I think 1 year, it may be last year, probably was last year because because we actually could fit the whole class in the lab and they did not close early like this year because we still had a little bit more money last year. And by the way, the chancellor of the entire community college district will be here on Thursday to talk about our budget situation. So I will give you, you guys can tell me, do you think it's going to be good news or bad news?
Good. Good news, all good news.
Do you think it's going to
Coming to this class or to the school?
just onto this campus. Yeah, he's going to be on campus and talk about the budget situation. Yeah, I personally don't think it's going to be like, guess what, guys, we got too much money. I need some help in spending all that money. Yep.
Is he just going to be referring to the budget, or is he also going to be talking about, because there's rumors of possibly summer being canceled?
I don't think summer is going to be canceled altogether, but there'll be heavy cut to the summer program. I believe the cut is at least 25%.
I mean, because they are posting a schedule, but then there's stuff being said on the news and everything about all the community colleges, so that's why I asked for clarification.
Some community colleges have already cut the entire summer schedule.
Okay.
But I think since
But
we
if it's
have,
posted, we're doing it?
yeah, if it is published, we are going to do it. The published schedule that we have for summer is already 25% after a 25% cut.
Last semester or the one before, they had it published and they still cut a lot of classes.
Yeah. this year is going to be very bad, especially spring 2013. So if you guys have any classes that you want to sign up for spring 2013, it's going to be particularly bad, because the mid-year cut means that it's unscheduled, it's unaccounted for. It's the cutting of the funding is unscheduled. So that means whatever classes we have scheduled for fall, we kind of have to let it stay. So we cannot cut our fall schedule. So now the fall schedule cannot be cut. So the cut has to come to the following semester, which is spring 2013. So spring 2013 has to absorb the original cut schedule for next year, as well as the unscheduled cut, the mid-year cut for this year. Yep. So it's going to be a little bit ugly. Most of you are pretty much done already because you're in the class right now.
So is the chancellor going to come speak to this class, or is he speaking like?
No. He's just going to be on campus, talking about the situation. I think he wants to calm people down and say that we're not going to lay off people. We're not going to have all kinds of bad things happening. Except the assembly programming class will now have it will be a 70 people class. Instead of 50, it will be 70 now.
It'll be in Rave Hall.
Do it in Rave Hall, exactly. Or online.
Yeah.
No physical presence required.
That wouldn't be terrible.
That might be a little bit difficult to teach this class.
Yeah.
Okay, here's question number 5. I knew I should not have mentioned the budget situation. You guys just. Okay, question number 5. What are the values in EAX and EBX after the following instructions? This one is kind of interesting. I kind of like questions like these. We have a move out instruction. Okay, it's very simple. It's going to make EAX 13, and then we have another instruction here that will make EBX 6. And then we have a push L instruction. It's going to push EBX on the stack. And then we have a move instruction to move EAX into EBX. And then we have a pop instruction to pop whatever is on the stack back into EAX. So what do you think this is going to accomplish?
They're swap.
Yeah, it's a swap operation. I'm using the stack as the temporary variable in a more conventional swap sequence. Yep. But this is the kind of thing that you can actually trace, because what you can do is you can actually draw the picture like what I did, so you can see what is on the stack, and then you can see what is being transferred from register to the stack, and then what is transferred from stack back into registers. So you can basically track this one down using the trace technique. Any questions about this one? No? Okay.
All of the questions are going to be like that?
Yeah, but since I have asked these ones already, I have to think of new ones.
Don't make it sound like it's easy.
Yeah, watch out for the.
This is like, oh my gosh, that's so hard.
Yeah, I don't know. I'm not so sure about this exam. Yeah.
Just to boost my spirits, please put that on the test. Don't worry, I'm not going to get an A, but
You shuffle them around.
Okay, question number 6.
Okay, I get some more stuff afterwards.
Yeah. Question number 6. Evaluate the following partial code, which means whatever is before and after does not matter. Assume L1 and L2 are defined somewhere other than the partial code listed. So in other words, L1 and L2 are not like right before this. And they are distinct, which means L1 and L2 are different labels. They do not go to the same place. What is the range of value in BL that will make this partial code continue execution at L2? Well, I'm not asking for one single value. I'm asking for a range of values.
Right. So
Okay.
you have to remember what GNA is looking for.
Exactly. So the first thing you have to do is to find out what JNA is going to do, and we will go to L2. The opposite will go to L2. Okay. So in this case, it's actually not too difficult, because if JNA is going to L1, it's basically saying JA will go to L2. So the question now is, what is A when you have a conditional branch instruction? Now remember, the test is open book, open notes. You guys can bring in your, my notes, your notes, sample programs, whatever you want to bring in is fine. So that means, it's jump above, right? JA is jump above. All right, so we'll go ahead and work this out, step by step. Okay, so JA to L2 which means jump to L2 if and only if BL is above 240. Okay? Now that's helping already. That's helping quite a bit already. Because you have to remember how to read these instructions, because the compare instruction is a subtraction instruction. And the subtraction is the second operand, the first operand is subtracted from the second operand. That's how the comparison works. Okay? Okay, so can you tell me the range of BL that is above 240? But hold on a second here. 240 is a tricky value because the most significant bit is set. So the question is, are we dealing with signed comparison or are we dealing with unsigned comparison? Unsigned, very good, because G and L are for signed, A and B are for unsigned. So we're dealing with unsigned, and unsigned makes it kind of easier because what is the range of unsigned values when you only have 8 bits to play with? 0 to 255, and here we want to say that BL has to be above 240. So the first value that will make this end up at L2 is going to be 241, and the last one is 255. Exactly.
It's a J and A, so what you want? The opposite of that?
The J and A will be the opposite of that, so that will go from 0 to 240, including 240 itself, because equal to is still not above.
It's greater, less than that.
Correct. Yep, go ahead.
I'm curious, how does binary number represent decimal number?
Decimal numbers?
Yeah.
You mean fractional numbers? We'll talk about that after we talk about the exam. Okay. Okay. Note to self. Meaning tag, because all of you can read this, so when you read note to self, it's not you, it's me. How fractions are represented. That's a good topic, okay? Okay, question number 7. We are close. We're pretty close. Read the following C code. If x is less than or equal to 3, increment x by 3. Okay. Assuming x is a 32-bit global variable, fill in the blanks in the following partial code in assembly to accomplish the same thing. Note that each underscore may take the place of a single letter or an entire expression. In other words, the underscore can be anything. All right. So what do you think?
Compare long.
Did I say it's signed or unsigned? Didn't say.
So we can just assume what we want, right? Yeah.
But that will only help.
Oh, I meant the other one. It's a floating point variable.
Okay, how about this?
Which one gives me the correct answer?
Okay, we'll make it easier. Unsigned int. Okay. All right. First of all, what goes here? L. Okay, very good. And then what do we put in these two places here? $3 goes here. And then what goes here? X. Because it is very explicit, X is a global variable and a static location. It's not on the stack. And then what do we put here? Okay, because it's unsigned, we want JA to go around the body of the conditional statement, and that's why it's the reverse of less than or equal to.
Right.
The reverse of less than or equal to is above. So this is correct because we are branching to L1 if and only if X is above 3. So that's good. And then what do we put here?
Add L.
Add L. Yeah, this part is the same as the one above. And then X here. Yep.
I understand that we're putting the L there for educational purposes so we could remember, but would the compiler still understand if we just
In this case, it is ambiguous. In this case, it is ambiguous because $3 can be a byte, can be a word, can be 32-bit long. X can also be a single byte location, a 16-bit location, or a 32-bit location. So this is completely ambiguous. When you say add without add L, It is only because by default it is using long that it will use the correct, width of operation.
So if you don't have like a register in there, like a 32-bit register, and you just use a memory location, and that memory location is just a byte, it will always, and you use an add instruction, it will always include an L in there.
The L is
Compiler.
implied, yes. That's the default.
Compiler will put an L, okay.
Correct. But you should not leave it up to the compiler or the assembler to imply it's a long operation, because sometimes you may not want it to be a long operation. Sometimes you want it to be a byte operation. If you don't specify the L, then it will turn into a long operation, and it's not obvious to you that it is a long operation.
Because I just came across a book that they completely don't use these. They just use add instruction and move instruction without ever using those. I guess they assume that the compiler would do that for you.
Well, that's because it's written by bad programmers, typically programming in Visual Basic.
But it works.
Well, because in Visual Basic you can actually turn on a lot of checking. You can basically make it not, forgiving, as much as you can. Same thing in Perl. You can turn on strict and warning. Yeah. How many people know that in Visual Basic you can do all kinds of nasty stuff? Like, when you have an assignment operation, on the right-hand side you can have a string, on the left-hand side you can have a like an integer, and it will happen. It will do the conversion automatically.
I cry when I see that.
Sorry?
Did I cry inside every time I see that? Automatic conversions.
Automatic conversion usually spells trouble later on. But I'm saving so many lines of code. I mean, why do we have to go through the explicit conversion and this and that? Because if you don't do it, it's going to bite you later. And it's going to bite hard too. Okay, question number 8. This is our last one. So let's go. All right. So you're given the fragment of code of C code as follows. Okay, so this is a fragment of C code. Assume that you also know that x is a 32-bit unsigned integer. So this time it is spelled out. It is unsigned. 32-bit. Ch is 8-bit unsigned. Both are global variables, which means they're statically allocated. Identify problems in the following implementation in assembly code and suggest changes to fix the problems. So there's still one, one question like that. You have to kind of fix the code. The code is double spaced to give you more space to write your own code. Be sure to indicate the proposed changes. Don't just tell me that this, just put a big rectangle around the whole thing and say, this is wrong. This needs to be fixed. All right, so this is the code corresponding to that. And this makes it a little bit harder to read. Let me see what I can do here.
Remove the top part.
Oh, I can see 7 of you are reading it at the same time. It's like Skittles. All these different colors. I think the dark green is probably a seaweed.
Seaweed.
Seaweed flavor. All right, so this is the code. So let me see what I can do to make this a little bit easier to read, because I can do kind of rapid duplicate. That's it. And then we drag this out. Get this one out, and then we can scroll one without scrolling the other one.
I love Chrome.
Yay! All right.
Question 1.
Oh.
Well, it would have been easy.
There we go. All right. So now we are talking. First of all, is the comparison done correctly? X is unsigned.
No.
If X is unsigned, the compare itself is okay, right? Because we are comparing X to 10, so the compare long is fine. But the JNL is incorrect. So how do we fix the JNL in this case? We are branching around, which means if X is not less than 10, we want to branch around. but we don't want to use L or G because it is unsigned. Instead of L, what should I use?
J and B.
J and B. Okay. B for below. J and C would work too because the carry flag and the borrow flag are actually the same flag. All right, so that's the first fix. And then inside, here, I have, I want CH to store X plus, the ASCII code of 0. So would that do the same thing? Oh man, it put in like, the actual back take instead of the forward take. So that's minor. Okay, we'll deal with that later. Okay, is the first instruction okay? Move X to CH. CH is a 1 byte variable, and X is a 4 byte variable. There are two things wrong here. The first one is memory operand. You can only have up to one memory operand with almost just any instruction. So what should we do here first? Break it up into two, right? But then we can also fix the other problem because we have to use a register. We are copying a 32-bit value into a 8-bit value here. You have to choose, okay? What you're choosing is, well, since one is a wider variable and the other one is a narrower variable, you have to choose. One way is to say that, well, we'll just move the least significant byte of X to CH. And the most significant 3 bytes will be lost, okay, simply because we don't have the storage to store that. Or you can use move long, which means not only are we moving the byte that we do want to move, but we are also moving 3 extra bytes. We have no idea who we are trashing, what we are trashing with those 3 extra bytes, but we are moving it. So the proper solution is to use a move byte here. Okay, so highlight it. And we want to change CH so it becomes a register. So we can specify, any register is fine, AL. Okay. And then in the next instruction here, we'll use move byte, AL to CH. Are we doing okay so far with this fix? So that means the next instruction also needs to be fixed because the first thing is we are adding byte instead of adding long. And then there's one more thing here. Yep.
So this isn't the register CH, this is a label CH?
CH is a variable, it's a static variable.
Okay.
It's defined by, CH colon dot byte 0 or something along that line. Okay, we're missing a $sign here. Okay. Hey,
Normally, in this case, you won't have to care because of you're just moving the byte. But normally, if you're like say moving along after this, would you want to make sure that your EAX was 0 before you did anything?
Yes, you do.
Yeah, in this case, you won't have to. Because
well, in this case, it doesn't matter because we are downcasting it, or we're truncating the expression. Yep.
You're moving the ASCII code 0, right?
I am adding the ASCII code of 0 to whatever is already stored in CH.
And assembly can do that with the single quotes?
Yes.
Okay.
Except, this quote has to be a forward quote as well, so I will see if I can change that. Yep, there we go.
are you going to trick us with those quotes?
No. With the quotes,
-5.
I did this, using Google documents because I was working on it on different computers, and the easiest way to work on, the same document on multiple computers is to use Google Documents.
I did some group projects with that, and they always messed up their quotes on you. So you have to go through and fix it.
Yeah, the quotes can be problematic. Okay, so now we have the second half, which is almost the same thing. So we have exactly the same thing here. Move byte. This is not very challenging anymore because we have seen all this stuff already. And then we move byte AL to CH. And then we have add byte here. And remember to use a $sign and also change that quote. But now we have, well, we have this one here. If you want to make, just make changes here, this would be the change. We just need to add a dollar sign here. That would do exactly the same thing. But if you want it to be more optimized, you could also do this too, and not have the second instruction. It will accomplish the same thing, because when we add the ASCII code of A and then subtract a constant of 10, it can be compacted, because these two, we can compute this value first, and then just say add this value to x. Yep.
Does the assembler put that in for you, or when you assemble it, does it still go through the processing of decrementing ASCII A? Because with 2 instructions, you're putting the work on the processor.
Correct. Now, when you combine these two, this is also called constant folding as a optimization technique. The computation is done by the assembler. Okay. So as far as your processor is concerned, it is just adding a constant to the other operand. All right. So that means it's a good optimization, because you're pushing the work as far upstream as possible. So the assembler pays a small price to do it once. But every time you execute this instruction, when you run the program, it doesn't have to compute the ASCII code of A minus 10 anymore. Cool. Yep.
So is that the same with other languages like C, C++?
It depends on the optimizer. When you compile a C program, if you specify uppercase O2 or uppercase O3, it will try to do optimizations like this. The compiler can be fairly smart with dealing with this type of optimization. Okay. Any other questions? No other questions? Okay, so let's go back and talk about how do we represent floating point numbers or fractional numbers, numbers that are not integers. Okay, that's a very good question. Well, the first thing that you can do. Okay, let me ask you a question then. If I want to represent money, but only using whole numbers, integers, how can I do it?
Pennies.
Let's say we're dealing. Exactly, we can count by pennies. Exactly. So we can do exactly the same thing with binary numbers. In other words, you have to figure out what is the smallest amount you want to represent, what is the smallest fraction, which is a power of 2, a negative power of 2 that you want to represent, and then you just change the unit to be a unit of that. So let's just say that you want to represent everything in, trying to figure out what to use to write here. I'm going to use a mouse pad. Okay, so you can say 1 over 256 is the smallest quantum to represent. Okay, so that means when you have a number like then 400 is actually representing 400 divided by 256. So that's one way. This is called fixed point calculation, because I guess in this case it's not a decimal point anymore, it's a binary point, but the point is always fixed. Okay, what is 400 in binary? I don't have a calculator that can do that easily.
You can't do that off the top of your head?
Well, we know it has 256. Okay, it's 256 plus, my arithmetic is bad, 144. And 144 is 128 plus, is it 16? Oh, there we go. That's not too bad. So we have 1, 2, 3, 4, 5, 6, 7, 8. And then we have to change this one to a 1, 2, and then the 16, that's 8, that's a 16 itself. So that's a binary number. Where's the binary point in this case? The binary point is right here. But it works the same way as in decimal, because what we can do is, this represents how much halves do we have. This represents how many quarters we have, 8ths, 16ths, 30 seconds, 64ths, 1/28 and 2/56. It works the same way as decimal numbers. You know, every time you move to the right-hand side, from the binary point, you are having the value that you are representing. That's called fixed point because you have to remember, in this case, you have to remember where the implied point is. It is not stored explicitly anywhere. But it is fast because when you use fixed point calculation, it is all integer calculations. So you can use integer multiplication. You just have to shift the point later on after the multiplication. Addition and subtraction requires no shifting at all because they preserve the location of the point itself. What about floating point numbers? How many people know or have heard of the term of floating point numbers? Okay, and those of you, okay. So with floating point numbers, okay, let me ask you one question. What is a limitation of this particular approach? You can only represent values of a certain range. Okay, no matter where the implied point is, you only can represent values of a certain range, which is not really handy for scientific calculations because when you deal with scientific calculations, you have to represent values that are over a huge range, instead of just a smaller range. So that means you have to be able to change where the point is located, and therefore we have the IEEE floating point notation. I'm not going to give you a lot of details on that, but I can show you easily where you can find more details. You just need to look up IEEE single precision floating point numbers. And Wikipedia has an extremely well-written article on this one. You can tell from the thumbnail, how long this is. And I just want to go to the representation part so that you can see the different portions of a 32-bit representation. Nope, that's not it. There we go. So this is how the different bits of a 32-bit number will be used. One bit is used for the sign of the number. In other words, we are no longer using 2's complement to represent negative value. We have one explicit bit to say whether the number is positive or negative, which also means that there are 2 zeros because you have positive 0 and you have negative 0. We have 8 bits to represent what we call the exponent, but it's really not the exponent. It's actually an offset added to the exponent. And then we have a significant precision, which is the actual value of the number, quote unquote, the actual value of the number. But in order to understand this type of representation, let me switch back to the mouse pad and ask you whether you understand the scientific notation of numbers. How many people understand the base 10 version of scientific notation? Okay, most of you do. Okay, so I can give you one particular example, like 5.623 times 10 to the power of 23. That's the scientific notation. Now, using the scientific notation, we can represent a huge range of number because what is controlling the actual order of magnitude? It's not this part, right? It's actually this part here. But this part, because when a small change to this part of the number changes the magnitude of the actual value represented, in a large amount. Exponential, exactly. And in this case, it's exponential with a base of 10, which is a lot. And then what about this value here? When you use scientific notation in base 10, what is always going to be the range of that side? It's going to be from 1 to 9.999999, because that's all you need. What if you have something that looks like this? Well, you can always quote unquote normalize it. By means of normalizing, I mean move the decimal point 1 over to here, and then just add 1 to the exponent. Okay. Now, but you can use the same approach with binary numbers. Okay, so when you use the same approach with binary numbers, then you end up with 1.0110, just binary number on the other side, and then it's it also has the same representation times 2 to the power of some power here. okay? But this power can be positive, it can also be negative, because if it is only positive, then you can only represent integers and larger values. But if you can go negative, then you can also represent very small numbers. Except in this case, the exponent, which is this component here, is not using 2's complement either. What it is doing is using an offset. So when you go back to the Wikipedia document and you go to the exponent portion, I think this may not be the right link. Nope, that's not the right link. Okay, the sign bit determines the sign, and then the exponent goes from negative 128 to 127. But it is actually an unsigned number. The exponent portion of a floating point number is an unsigned number. So the actual exponent is whatever the 8-bit is representing, and then you have to subtract 128 from it to get the actual exponent that the number is representing. Are we doing okay so far? That means if the exponent, if those 8 bits allocated to the exponent is exactly 128, which is 1 followed by 7 zeros, that means the exponent is actually just 0. No, it's 0 because you have to subtract 128 from that value. Are we doing okay so far? Kind of.
Makes sense, but that's not what they're saying.
It's not.
No, they say 127 is actually 0.
For this case, an exponent value of 127 represents the actual 0.
Wikipedia is talking about it in terms of you looking at it. The actual storage is the
Right.
8-bit unsigned integer. That's the actual way it's stored. They're trying to talk about the way you look at it. It's all that. Wikipedia is not the site to look at. It's not
No,
the
I know that.
But yeah, they're talking about it and how someone would try to look at it and read it on how it's done.
Okay, that was one hand. Yep, go ahead.
This would give floating point numbers a much larger range, both for integer values and fractional values than even like a long, right?
Yes, but you are paying a price for that because you only have 32 bits, which means you still only have about 4 billion possible values they can represent.
Exactly. But you can exactly to that precision, but you can
exactly. You're
represent-
paying the price in precision. So we are going to the significant, precision part. Yep.
This is just out of curiosity. Professor Fox has a program he runs, and it starts out as a long number, but gradually as he runs the program, it becomes incredibly large, and it has that notation when printed, e to the whatever. So is the program casting it to a double at that point, if it exceeds the bounds of long?
It depends on what is the programming language used in that case.
It was C.
It was C.
You didn't implicitly cast it though, but it printed out correctly. So it must have been the cout object did it or something.
I do not know that cout would automatically cast a long to a floating point, but it prints it out. Okay. So anyway, this is how the number is actually represented. We have 32 bits to play with. Bit 0 to bit 22 is basically the significant portion, but it has an implicit 1 in front of it. In other words, even though we only have 32 bits, it has an implicit 1 in front of this bit here. And then we have the exponent, which is 8-bit only, and then we have a sign at the end of that. And that's how a 32-bit single precision floating point number is represented.
This is the sign
chopped
for
up.
the number, not the exponent, right?
Sorry?
The sign is for the number, not the exponent.
The sign applies to the entire number, not the exponent. Right. Yep. So did that answer your question about how we represent fractional numbers and stuff like that?
Oh, the reason I went into that is because I was learning about compare instructions. When you say decimal number, does it count as an integer when I compare, or
Say that again.
or comparison instruction? When you put one of the numbers, a decimal number, does it count as an integer, or does it
I
count
have
as-
not tried that. It will not accept it?
It would either not assemble or truncate, because there's a whole different set of instructions for the
Yeah. Any other questions about the floating point number representation. It's a little bit out of the scope of this class, because we only deal with integer instructions. But it is nice to know a different way of representing values.
Don't try and explain how you can't store 0.3 for exact values.
Yep, or 3.
Or 3 for that matter, yeah.
Yeah, certain values that seems to be it seems to make sense that you should be able to represent as a whole number. It cannot be represented.
Correct.
Yep. The test is 1 week from today, so that will be next Tuesday. Yep. All right, I'll see you guys on Thursday.